Assalamu alaikum students. In this lecture number 9 we will discuss about the theory of alpha decay and its quantum tunneling. Uh, so, here is just introduction which we have already discussed in the last lecture. The alpha decay is the type of radioactive decay in which we will get alpha particle as an emitter and a daughter nucleus, and the mass number of the daughter nucleus is reduced by 4 and the atomic number is reduced by 2, and also the neutron number is reduced by 2 because the helium particle alpha particle has 4 number of nucleons in which 2 are protons and 2 are neutrons. As an example, uranium-238 decays to form thorium-234, and you can see the A number is decreased by 4. In the equation you can see below, the X, the parent nuclei, is decaying to daughter nucleus Y plus the alpha emission. So here is an example of uranium equation for uranium-238 decay, and you can see the A number is decreased by 4 and the proton number is decreased by 2, and we have emission of the alpha particle. So in this lecture we will discuss about a theory in which it is assumed that the alpha particle is already formed within the nucleus, parent nucleus, and wants to eject from the potential of the parent nucleus, and it has energy less than the Coulomb barrier, but still we have alpha decay, and this cannot be explained by classical physics, and we need the concept of tunneling from the quantum physics, and we have to find the transmission probability of the alpha particle from this barrier, Coulomb barrier. So here is a figure in which you can see that the alpha particle is tunneling through the unequal Coulomb barrier, and that this transmission probability depends upon the energy of the alpha particle, and the alpha particle gets energy from the reaction Q value, and as we already discussed that the reaction Q value will be distributed between daughter nucleus and helium nucleus, and the most of energy will be taken by helium nucleus because of its less mass, and 98% of energy will be taken by alpha particle. So it's important to know about the energy of the alpha particle, and in 1928 George Gamow and independently Ronald Gurney and Edward Kondo solved this theory of alpha particle decay using quantum tunneling process. They assume that the alpha particles and daughter nucleus already exist within the parent nuclei and want to eject from it. So in the coming slide we will discuss how it works. So in the in the right hand figure you can see that the alpha particle has already energy equals to Q, and the B is the capital B is the Coulomb barrier, and if alpha particle wants to surmount the Coulomb barrier, it needs energy equals to B minus Q, and then classically it can surmount the barrier. But still we have alpha decay process in practical, so there is a tunneling probability which is shown in dashed line, and a small a is the a radius of the parent nuclei, and alpha particle is present within the parent nuclei, and B is the point after which the alpha particle will be free from the potential of the parent nuclei. So alpha particle is bound within the parent nuclei and it wants to eject from it. Here we have calculated the alpha particle, the Coulomb barrier at r is equal to a distance, and which is the 1 over 4 pi epsilon naught z prime e square over a, and z is the charge on the helium nucleus and the z prime is the charge on the daughter nucleus. So as our you can see our potential barrier is not smooth and the height is changing with radius with the distance r, and also the width is changing with the distance r. So we have to find the average height of the Coulomb barrier and the average width of the Coulomb barrier. And if we can see the Coulomb barrier height at r is equal to a, if you can see the height is start from where the alpha particle is there, it's b minus q, and if we move forward in the direction of r, you can see the height of the barrier is reducing, and at the point b it becomes 0. So average height will be b minus q plus 0 over 2. So we have b minus q over 2. So the width of the Coulomb barrier at r is equal to a is 0. You can see horizontally, you can see the width is 0 at the this point, and at if we move forward in the direction of r, you can see at point b the width of the barrier is b minus a. So the average width will be b minus a plus 0 over 2. So why we have calculated average height or average width? Because we can compare it with the rectangular barrier. You can see in the figure we have compared it with the rectangular barrier, which has the width of a minus 0, which is a, and the height is constant, which is v naught, and in our case the height is changing, so we have taken average height, and also width is changing, we have taken average width. So why we are doing it? Because in the textbook the transmission probability of the particle through this rectangular barrier is already calculated in chapter number 2, and we can use the same equation for our barrier. So E is the energy of the particle in rectangular barrier. In our case, the energy will be Q. So here is the transmission probability which is taken from chapter number 2 for the particle having energy E less than the V naught, and if we want to transform it for our irregular barrier, then we have to change V naught to B and E to Q and A to B minus A over 2, because in our case the average width is B minus A over 2, but in rectangular barrier the width is A. So after this substitution, we will get equation which is written below. So in the next slide, you can see just by replacing the sine hyperbolic scale, if we take all this x, we can change into the exponential form, and third equation, you can see the c is just a constant, because b q they are constant, 4 is taken out, and they are all constant. And now we have competition between these constant and the exponential term, and the most influential exponential term is the e to power 2k2 bracket b minus a over 2 bracket closed. And because the k2 multiplied by b minus a over 2 is a big number, and if we take the exponent of the big number, we will get a big number which is very big, and the second term is e to power minus 2k2 bracket b minus a over 2 is becomes 0, and we have a dominating term is only e to power 2k b, in brackets b minus a over 2, which is so big that c is just nothing cannot do with it, and plus 1 is also nothing. So if we'll take this and it will go to up, and we will get a probability transmission probability P is equal to this e to power minus 2k to 1 over 2b minus a. So this transmission probability, if it uh, put some values for some specific uranium or 238, it is very small, but still it exists, and we can see the alpha decay process in these elements. So this is the transmission probability of alpha particle from the periodic layer. So thank you, students, and so please read your text.